In 1405 AD, a fleet of ships left the coast of China, carrying millions of gallons of fresh drinking water distributed across localized logistics hubs. Months later, deep in the Indian Ocean, thousands of miles from the nearest river, that water was still clean, still cold, still safe to drink. No chlorine, no chemicals, no filtration machines. At the exact same moment in history, British sailors were prying open oak barrels mid-voyage and finding black slimy liquid crawling with worms. They drank rum instead. When the rum ran out, they drank the rot. Half the crew died before they ever saw land again. Same ocean, same sun, same problem. One civilization solved it permanently. The other spent the next 400 years dying from it. This is the engineering story of how the Ming Dynasty Navy built a water preservation system so precise, so layered, and so effective that it outperformed every Western alternative until the industrial age. And by the end of this video, you will understand exactly how to replicate its core principles in your own home for a fraction of what you currently spend on water treatment every year. Liquid stagnation and subsequent spoilage are directly dictated by container material dynamics. For 4 centuries, Western naval architecture relied on oak cooperage. Leaguers holding 150 gallons, butts holding 110, and hogsheads holding 63. These barrels were the global standard. Every navy used them. Every merchant fleet depended on them. And every crew that sailed more than 3 weeks from shore paid the price for it. Here's the problem with wood. It looks solid, but under a microscope, oak is a porous sponge, a dense network of microscopic channels and fibers designed by nature to absorb and transport water. The moment you fill a wooden barrel, the walls begin to drink. The wood becomes saturated. In the dark, damp hold of a ship rolling through tropical heat, that wet wood becomes a perfect incubator. Bacteria move in. Fungi follow. Within 14 to 21 days, the water inside is no longer water. It is a living colony of rot. The bilge made it worse. Casks were stored deep in the hull, often sitting directly in stagnant bilge water. A foul mixture of seawater seepage, rat waste, and decaying food. The porous wood absorbed contamination from the outside just as readily as it bred it from within. The barrel was not protecting the water. It was poisoning it from both directions simultaneously. The consequences were documented and catastrophic. Cholera, typhoid, and dysentery swept through European ships on long voyages, killing up to half the crew before landfall. Western navies tried everything. They added brandy to slow the rot. They burned sulfur inside empty barrels to sterilize them. Some captains dropped lead sheets into the water, believing the metal would purify it. The lead did not purify the water. It poisoned the crew instead. The deeper problem was structural. European exploration was physically capped by the lifespan of a wooden barrel. No ship could venture more than 2 to 3 weeks from a freshwater source on land. The ocean was not the barrier, the container was. And the reason the container kept failing was simple. The West chose an organic material to hold an organic resource, then acted surprised when nature took its course. The Ming Navy understood something different. They understood that the container is not just a vessel, it is the first line of defense, and they built theirs accordingly. The Ming Navy did not try to fix the wooden barrel, they eliminated it. On long-haul voyages, wooden water storage was banned. In its place, Chinese shipwrights deployed what they had been perfecting for over 1,000 years. High-fired stoneware ceramic vessels, known as martaban jars. These were not decorative pots. Some stood over 3 feet tall. They were built in the dragon kilns of southern China. Massive, tunnel-shaped furnaces that stretched up hillsides and used the natural draft of the slope to reach temperatures that European kilns of the same era could not match. The clay itself was a precise blend of river clay and quartz sand, chosen for its density and thermal stability. Prior to vitrification, the interior surfaces were sealed with an iron-rich, feldspathic clay slip glaze, completely free of soluble lead variants to prevent toxic, heavy metal leaching into the supply. Then the kilns were fired to over 2,200 degrees Fahrenheit. At that temperature, something fundamental happened to the clay. The silica in the walls melted. Not softened, melted. The molecular structure of the ceramic collapsed and refused into a continuous, non-porous solid. This process is called vitrification, and the result is not clay anymore. It is glass, dense, sealed, and completely impermeable. The interior glaze fused into a smooth, glassy armor plate with no accessible surface area. No pores, no cracks, no organic fibers. Bacteria arriving at that surface had nothing to anchor to, nothing to feed on, and nowhere to hide. The biofilm that destroyed European oak barrels in 2 weeks could not form on vitrified stoneware in 2 years. The thick, dark walls of the jar did 2 additional things. First, they blocked all sunlight from reaching the water inside. Without light, photosynthesis stops. Algae cannot bloom. The water stays clear. Second, the thermal mass of dense ceramic absorbed heat slowly and released it slowly, keeping the interior temperature significantly cooler than the surrounding air, even on a sun-baked deck in the Indian Ocean. Portuguese and Dutch traders who encountered these jars 2 centuries later paid premium prices for them. Their own records noted that water stored inside martaban jars remained, in their words, sweet and cool indefinitely, even in tropical conditions. They did not fully understand why. The physics did not care whether they understood it or not. But the jar alone was not enough, because a glass-lined ceramic vessel, however well engineered, is still brittle, and a 2,000-ton wooden warship slamming through a typhoon generates forces that will shatter brittle objects against each other in minutes. The Ming engineers had already solved that problem too. A single specialized logistics vessel within the fleet routinely allocated hull space for over 50,000 gallons of potable water storage. This represents roughly 400,000 pounds, or 200 tons, of liquid mass shifting dynamically inside a wooden hull on an open ocean. If this mass shifts unhindered during heavy seas, the kinetic energy generated threatens to capsize the vessel. Naval engineers today call this the free surface effect. It is one of the most dangerous forces a ship designer has to manage. The Ming Navy was managing it in the 1400s AD. Their solution was built into the bones of the ship itself. Chinese shipwrights divided the lower hull of the treasure ships into as many as 16 separate, watertight compartments using thick timber partitions called bulkheads. Each compartment was sealed from the others, structurally independent, watertight, and isolated. The design was inspired by the natural internal architecture of bamboo, which uses chambered nodes to distribute stress along its length without catastrophic failure. This compartmentalization did something elegant to the physics of the water. Instead of 200 tons of liquid moving freely across the entire hull, the water was locked into 16 separate rigid cells. The fluid could not build momentum across the ship. The free surface effect was neutralized by the architecture itself. The ceramic cisterns were then lowered into these individual compartments, but they were not simply placed inside and left to rattle. Workers packed the gaps between the jars and the wooden walls with a precise mixture of dry river sand, charcoal, and braided straw. This packing layer acted as a macro-scale suspension system. When the ship rolled in heavy seas, the sand and straw absorbed the kinetic impact, preventing the jars from vibrating against each other or against the hull. The ceramic never touched wood directly. It was always cushioned. The weight distribution was equally deliberate. The water mass was locked at the absolute lowest point of the ship, directly above the keel, below the waterline. This placement lowered the vessel's center of gravity significantly, making the entire ship more stable in high winds and rough water. In severe storms, the crew could flood empty compartments with seawater to add additional adjustable ballast, further lowering the center of gravity on demand. The West would not adopt watertight bulkhead compartmentalization in shipbuilding until the late 1700s AD, nearly 4 centuries after the Ming fleet had already made it standard practice. The structural problem was solved. The water was sealed in vitrified stone, locked inside a compartmentalized hull, cushioned against impact, and stabilized as ballast. But even inside a perfect container, water exposed to air over months will eventually go stale, lose its oxygen, and become vulnerable to airborne contamination entering through the fill hatch. The Ming engineers had a solution for that too. The first 3 layers of the Ming water system were passive and structural. The 4th layer was active, a continuous chemical-free biological defense built into the storage architecture itself. It operated on two mechanisms working simultaneously. The first was metal. For officer-class water storage, the interior walls of the ceramic jars were lined with copper sheeting, or pure silver plates were suspended directly inside the water. This integration functioned as an active biochemical barrier based on historical empirical observations of oligodynamic sterilization. The Persian king Cyrus the Great, who ruled in the 500s BC, refused to drink water that had not been boiled and transported in solid silver vessels. Ancient Greek physicians noted that water kept in silver containers did not develop the foul smell that killed sailors. Chinese, Indian, and Middle Eastern scholars all recorded the same observation independently. Metal kept water sweet. Modern microbiology explains exactly why. When water contacts copper or silver, the metal continuously releases microscopic charged ions into the liquid. These ions seek out single-celled organisms. They bind to the sulfur-rich proteins in bacterial cell walls, physically rupturing the membrane and halting the cell's ability to reproduce. The process is called the oligodynamic effect, and it operates continuously, passively, and indefinitely, as long as the metal is present. Modern laboratory testing confirms what ancient observers recorded empirically. Water stored in copper or silver vessels is sterilized of E. coli, Vibrio cholerae, and Salmonella typhi within hours. No heat, no chemicals, no energy input. The metal does the work by existing. The second mechanism was carbon. The fill openings of the storage jars were capped with compressed layers of activated bamboo charcoal. To produce it, raw bamboo was pyrolyzed, heated in low-oxygen kilns until everything except the carbon burned away. The result was a material that was 85 to 98% pure carbon, and its internal structure was extraordinary. At the microscopic level, activated charcoal is a dense network of millions of tiny pores, so many that a single gram of activated bamboo charcoal has an internal surface area larger than a tennis court. As air moved in and out of the jar through this charcoal cap, the pores acted as a physical trap. Airborne mold spores, dust particles, and organic compounds were captured before they could reach the water. Dissolved gases and odor compounds already in the water were adsorbed, bound to the carbon surface, and removed from the liquid entirely. The water that passed through the charcoal layer came out cleaner, clearer, and better tasting than it went in. But the charcoal did something else that no Western filter material of the era could match. As it slowly interacted with the water, it released beneficial minerals back into the liquid: potassium, magnesium, calcium, and sodium. These are the electrolytes a crew loses through sweat during hard physical labor in tropical heat. The charcoal was not just filtering the water, it was restoring what the sailors needed to stay functional. Raw bamboo also contains a natural antimicrobial compound called bamboo kun, which bonds to the plant's cellulose structure and persists even after the charring process. The charcoal cap was not just a mechanical filter, it carried a passive biological defense of its own. When the charcoal became saturated, the crew did not replace it. They laid it in direct sunlight for 3 hours. Ultraviolet radiation burned off the trapped organic material and reactivated the carbon structure. The filter was renewable indefinitely at zero cost. Step back and look at what the Ming Navy had built. Vitrified stoneware sealed the water away from organic contamination. Copper and silver ions neutralized any biological threat from within. Activated bamboo charcoal filtered the air entering the jar, absorbed impurities, restored minerals, and regenerated itself in sunlight. Every layer reinforced every other layer. The system required no ongoing chemical input, no external energy source, and no consumable supplies. It ran on material physics alone, and it kept 27,000 men alive across tens of thousands of miles of open ocean. There is one more layer to this system, and it is the one that most clearly illustrates how Ming engineers thought about problems. The treasure fleet carried enormous quantities of fine blue and white porcelain from the imperial kilns of Jingdezhen. Fragile ceramic plates, cups, and bowls packed for trade across the Indian Ocean. Transporting thousands of breakable ceramic pieces across months of rough ocean travel was a serious logistical problem. Dry straw and cloth packing rotted quickly in the damp hold. Rigid wooden frames added weight without absorbing impact effectively. The infrastructure prioritized dual-use material logistics. Long-haul vessels transported dense reserves of dry, high-protein mung beans and soybeans packed tightly around dry porcelain trade goods to absorb shock and eliminate internal shifting during transit. Upon rotation, these dry legume reserves were systematically drawn from the dry holds and moved to the subsurface hydroponic irrigation grids. By introducing fresh water to the isolated seed trays, the embryo activated, automatically synthesizing L-ascorbic acid to safeguard the crew against systemic collagen degradation. The British Navy would not mandate citrus rations to prevent scurvy until 1795 AD. The Ming fleet was generating fresh vegetation inside their subsurface hydroponic bays 3 centuries earlier. One system, 2 problems solved simultaneously. Fragile cargo, protected. Crew nutrition, maintained. No additional weight, no additional space, no additional cost. This is the pattern that runs through every layer of Ming water engineering, the refusal to solve one problem when the same solution can solve 2. The Ming water preservation system was not abandoned because it failed. It was abandoned because the global economy changed what it valued. And a system that runs for free does not fit inside a model built on recurring revenue. In the 1800s AD, the logic of empire shifted from resilience to throughput. Shipping companies wanted lighter vessels, faster transit times, and maximum cargo volume per voyage. Ceramic cisterns and sand packing are heavy. They occupy hull space that could otherwise carry profitable goods. Iron water tanks were lighter, cheaper to manufacture at industrial scale, and easier to install in standardized ship designs. The water quality problem that ceramic and carbon had solved passively was then resolved chemically. Chlorine was introduced as a water disinfectant. In the early 1900s, chemical treatment tablets followed, replacement filter cartridges, bottled water. Each solution converted a material problem, one that could be solved once, permanently, with the right container, into an ongoing consumable expense. This is not a conspiracy. It is a structural outcome. A passive system built from stone, silver, and charcoal has no supply chain. It generates no recurring revenue. It creates no dependency. A chemical system that requires monthly resupply creates permanent customers. The industrial economy did not suppress the Ming system out of malice. It simply had no financial mechanism to sustain it. The American household now spends between $400 and $1,200 per year on water-related chemicals, replacement filters, and bottled supply. To solve a problem the Ming Navy solved permanently 6 centuries ago with materials that cost almost nothing and last a lifetime. The knowledge was never destroyed. It was made inconvenient to find. The Ming preservation system is not a museum piece. Every component is available today, and the translation to a modern off-grid water supply is direct. Replace plastic and thin-walled metal containers with food-grade glazed stoneware crocks. Sizes from 5 to 50 gallons are available from Heritage Potteries and pickling suppliers for $80 to $300. They block UV, resist biofilm formation, and last for generations with no maintenance. Integrating the ionization layer requires dropping a high-purity silver asset or a copper mesh array into the storage matrix. This passively initiates the oligodynamic sterilization cycle, running continuously without energy degradation for decades. Cap your storage with activated carbon, food-grade activated charcoal, bamboo or coconut shell, used as a filtration layer at the fill inlet, will absorb organic impurities and restore mineral content. Regenerate it in direct sunlight every few months. Replace it annually if you prefer. The cost is negligible. If you are storing water on a vehicle, a boat, or in a seismic zone, pack cushioning material, dry sand, gravel, or dense foam around your containers. The bulkhead principle applies at any scale. The one-time cost of a Ming equivalent 50-gallon household water reserve runs between $150 and $400. The ongoing cost is effectively zero. The conventional approach, chlorine tablets, replacement filter cartridges, bottled backup, runs $200 to $600 per year, indefinitely, for an inferior result. The Ming engineers did not build a complicated system. They built a complete one. Every layer reinforced every other layer. Every material was chosen for permanence, not consumability. Once built, it required nothing from the outside world to keep working. That is the principle. That is the tactical wisdom. And it is 600 years old. The Ming Navy crossed the Indian Ocean with 27,000 men and millions of gallons of total water reserves, and lost none of them to systemic dehydration. They achieved this via vitrified clay engineering, charged metal ionization, and pyrolyzed carbon filtration networks structured to run indefinitely on material physics alone. The West spent the next 4 centuries dying from a problem the Chinese had already solved, then spent the following century building a chemical industry to resolve it at a profit. The knowledge was always here. It was just buried under the cost of the alternative. If recovering this kind of engineering history, the kind that actually works, costs less, and was set aside not because it failed, but because it couldn't be monetized, is the kind of content you want more of, then subscribe. Every video on this channel is built on the same principle. The old answers are still here, and most of them are better than what replaced them.